One of the most beautiful things about science is this. One day, someone comes along with an idea so extraordinary, so radical, that it changes everything.
First comes the wave of rejection. That's impossible, say the scientists, clinging tightly to tradition.
Then a few brave voices start saying, wait, this actually makes sense. And then, well, you know how the story goes. Einstein knew this all too well. His theory of relativity blew everyone's mind.
But in the end, one of its simplest consequences is something we use every single day, GPS, and it works almost flawlessly, thanks to relativity.
And today, we're going to talk about another one of those ideas. One that's hard to grasp, and one that delivers a serious blow to everything you think you know.
Here's the claim. Right now, right where you are, a perfect mirror of you, your surroundings, your entire existence, may be ruling over a hidden reality.
Mirror atoms, mirror planets, mirror lives, mirror you. A universe where cars drive in reverse and clocks tick backward. A mirror universe. And here's the thing. This mirror universe might not be far away at all. It could exist right here, woven into the very fabric of our own space-time, like the other side of a coin. Just as heads can never see tails, a universe we've never glimpsed may be unfolding alongside ours, right now, as we speak. Sounds crazy, right? The very thought of it feels absurd. If we saw this in a science fiction movie, we'd say, oh, come on, that's too much. The fun is over. Now we're getting into real science. But here's the thing. There is a very real, very important problem that's been nagging at today's physicists. Specifically, a big problem with the neutron, one of the fundamental building blocks of every atom, and therefore, everything you've ever known. 9 seconds. That's right. Some neutrons occasionally vanish for 9 seconds. They just disappear.
Where do they go during those 9 seconds? That's the question causing serious confusion. Let's take a look at what we're really dealing with.
Now, this story gets a bit complicated, as you might expect, so let's take it step by step in 4 stages. You'll understand exactly what we're talking about. First, let's go back 400 years to the moment a man pointed a telescope at the sky for the very first time. Before that, all our observations were made with the naked eye, and honestly, we were doing a pretty impressive job. They figured out the Earth was round, and around 200 BC, Eratosthenes managed to measure the Earth's circumference with just a 1.6% margin of error, with no technology, just brilliant thinking. But in 1608, a Dutch optician named Hans Lippershey invented the first telescope. A few years later, Galileo refined the design and opened an entirely new era in astronomy. Through this telescope, he saw the moons of Jupiter. He observed that Venus had phases, just like our own moon. He had proven what Copernicus and a few brave thinkers before him had only claimed, that Earth revolves around the sun. With Galileo, a brand new door to the cosmos swung open for all of humanity. Next, in our second step, we come across a discovery that happened entirely by accident. In 1896, French physicist Henri Becquerel placed a small metal cross between some uranium and a stack of photographic film. His intention was to prove that light couldn't pass through to the film. But when he developed the plates, there it was! A crisp, unmistakable image of the cross, burned into the film by something invisible. Today, this might sound like common knowledge, but back then, It was absolutely mind-blowing. Uranium was emitting radiation, something nobody even knew existed.
And with this discovery, the very first seeds of quantum mechanics were planted.
Fast forward a bit in time, and we arrive at step 3, dark matter.
In 1933, Swiss astronomer Fritz Zwicky turned his attention to a galaxy cluster. The individual galaxies within it were orbiting a common center of gravity, buzzing around it like bees around a hive.
Zwicky set out to calculate the total mass of the entire cluster. He measured their brightness, because brightness is directly linked to mass, and from that, he calculated the total gravitational pull. Then, he measured how fast the galaxies were spinning.
But there was a problem. The galaxies were moving way too fast.
When he calculated the mass and gravitational pull of these galaxies, it wasn't nearly enough. The gravity was far too weak to hold them together. These galaxies should have been flung apart long ago.
But something invisible was holding these massive galaxies together inside the cluster. What was it?
There had to be an unknown source of gravity, powerful enough to bind all that mass together around a common gravitational center.
And this would become our very first clue about dark matter. You already know the rest of that story. We covered it in a separate video.
But now, let's get to the final step, the step that hints at the existence of mirror universes. Free neutrons.
A very strange phenomenon. Now, almost everyone remembers this from school physics. An atom has two basic parts, a heavy nucleus at its center and electrons orbiting around it.
The nucleus itself is made up of protons and neutrons.
I won't get into the standard model. We already covered that. For now, this is all we need to know.
Because this is where things get really interesting.
When protons and neutrons are together inside the nucleus, close to one another, everything is fine. They're perfectly stable and can stay that way for billions of years, as long as nothing disturbs them.
But the moment you pull a neutron out of that partnership, it can't survive on its own. In roughly 15 minutes, it decays, breaking apart into protons and electrons.
Oh, kind of a sad story, really.
But wait, it gets even more complicated.
Depending on how you run the experiment with free neutrons, the results change. The decay time is different, and that makes no sense whatsoever. A neutron is a neutron. The results should be the same.
For example, one way to measure how long a neutron takes to decay is to place a few neutrons in a weak magnetic field. In this setup, a neutron decays in an average of 14 minutes and 39 seconds.
But when you run the experiment differently, the results go haywire.
We see this most clearly in nuclear reactors. In reactors, neutrons are set free, and those free neutrons take an average of 14 minutes and 48 seconds to decay.
So where on earth did this 9-second gap come from?
You might think, what's the big deal? It's just 9 seconds. But physicists have repeated these experiments thousands of times, accounted for every possible variable, and still they can't get rid of those 9 seconds.
And those 9 seconds are one of the most hotly debated mysteries in all of physics.
And some quantum physicists believe we can explain those 9 seconds, that lost time, with a mirror universe.
For instance, in the first experiment, the magnetic field might be allowing a neutron to slip into the mirror universe. The neutron spends some time there and then pops back into our universe.
In other words, the neutron is spending part of its short life in the mirror universe. According to physicists, if even 1% of neutrons make this jump, the 9-second discrepancy is completely resolved.
And this jumping between universes might explain another mystery too. Dark matter.
Yes, the dark matter we've never been able to detect might be hiding in this mirror universe.
If our theories about the early universe are correct, and the mirror universe formed during those same early moments, then according to calculations, this mirror universe would be a much, much colder place than ours.
And this temperature difference could mean that some particles have crossed the line separating the mirror universe from ours, never to return. In fact, the calculations tell us that for every single normal particle in our universe, there should be 5 particles in the mirror universe.
1 to 5.
Does that ratio remind you of anything? Yes. Scientists researching dark matter had already predicted that there's 5 times more dark matter in the universe than normal matter.
So then, we found dark matter? Mystery solved?
Unfortunately, it's not that easy. For now, this is still just speculation.
But a particle physicist named Leah Broussard is determined to put this idea to the test. She designed an experiment to do just that.
The design is elegant. They build a wall so thick and so dense that no neutron could ever pass through it physically. And behind that wall, they place a neutron detector.
Under normal circumstances, that detector should pick up absolutely nothing. But if it detects something, well, then there's a very interesting possible explanation.
The neutron fired at the wall might be jumping into the mirror universe just before hitting the wall, traveling through the mirror side, and then popping back into our universe right at the detector.
The experiment is largely ready at this point, but as far as I know, reliable results haven't been published yet. When they do find something, I'll definitely let you know. So in summary, if that detector picks up a neutron, we would be one giant step closer to understanding dark matter, another universe, and that annoying 9-second discrepancy, all at once. But there are some problems with these claims and experiments. First and foremost, humanity doesn't yet have the technology or the accumulated knowledge to fully understand the quantum universe and how particles truly behave. Yes, that might sound strange, but we still have a very long way to go. Maybe, no matter how many times we try, our limitations are simply giving us inaccurate results when it comes to neutron decay.
Or maybe, just maybe, we really are talking about a mirror universe, or even many other universes beyond that. I guess we'll just have to wait and see, together. And as always, until we meet again, I'm glad you're here. Sending love.